All right, so our goal is to begin looking at inhomogeneities in the universe. Okay, and any questions up until this point? Right, so as we discussed maybe in the very first lecture, if we look at our universe, let's say I plot density versus position, and let's first of all, let's make a comment about the early universe. So if we imagine this is somehow the mean density, I'll call rho bar. So up until this point, we just called it rho, but now I'm going to put bars on top of the mean values, or what we'll call the background values. At least in the very early universe, the true density is a little different than this. It fluctuated around that. But the fluctuations are very small, right? So let's say I draw it like this. Over densities and under densities. And these changes, so I could write rho as the background value plus a little perturbation that I'll call delta rho. And we can measure the fractional change we'll later write as delta itself. So it's delta rho over rho bar. And these fractional changes here are very tiny in the early universe. So something on the order of 10 to the minus 5 to 10 to the minus 4, something like that. Okay. So early universe. This delta is like 10 to the minus 5, 10 to the minus 4. There are many, many little wiggles you can draw, many, let's say, waves you could draw. And so it depends on the wavelength you're interested in as to the specific value, but very tiny numbers. Okay, now this picture has to grow, right? If that was our universe today, it would not look like our universe, because like, where are the galaxies and so on? Where's the really inhomogeneous stuff in it? So that has to form out of gravity. So over time, you can imagine that these overdensities are going to want to grow, right? We have an overdensity, gravity is going to start to pull in the surrounding material. So the overdensities somehow want to grow and become more overdense, and they're going to suck in their environment. So the underdensities are going to become more underdense as well. Okay, so you can imagine that it would somehow evolve like this. Just as a cartoon. And then this picture, you imagine this keeps on evolving. Okay, so somehow at late times, we've radically changed what the universe looks like to be, I don't know, something like this, loosely speaking. Okay, regions where you can even go much higher than that. Right, regions where, let's say, there are galaxies here and clusters of galaxies. Where these little overdensities in the early universe have somehow grown and grown and grown under gravity to give us huge overdensities. And this picture, though, if we kind of zoom out on sufficiently large scales, we could kind of do some averaging here as well, that we talked about in the first lecture. But we start off where, even on relatively small scales, we have very close to homogeneity we've been discussing with tiny little perturbations. So our challenge is to go from this somehow to this. Okay. And since we start off at such small fluctuations, for a while we can evolve these equations, we can use linear equations to evolve, although over here it's highly nonlinear. So we can only push our analytical formulas that we'll be developing the next couple of lectures so far, but they'll be quite useful to tell us a lot of information. There's a question?
Yeah, when the early universe.
Yeah, so we're going to, early universe we can think of as even potentially earlier than that. So we could imagine these little fluctuations at the sort of 10 to the minus 4, 10 to the minus 5 level that I drew in blue. We could even imagine that being laid down as early as you like. So say when the universe was a second old or something. So what caused those initial fluctuations is a topic we'll discuss later, or at least we have a candidate theory for what laid that down in inflation. We don't know for sure if that's right. But yeah, you can lay these down at very early stages. And your question about CMB is a really good one because for certain components of this, not a lot is going to happen until CMB. And for other components, something interesting will happen until even during that phase. So there'll be a distinction. See, I've drawn here as though there's just one row, but I should really draw the row of the baryons and the row of the dark matter. Okay, we're going to be talking about matter evolution primarily. We could also talk about the row of the photons. We're mainly going to talk about the evolution of matter. And the way that the baryons evolve versus the way the dark matter evolves will be different because those baryons are talking to the photons for those first 380,000 years. So that will affect things. And the dark matter does not talk to that, so they will evolve more simply under this picture. And indeed, the baryons, since they're coupled to the photons, will exhibit pressure. They'll have to worry about a pressure force. So yeah, so there are three things at play here. There's, well, pressure that I just mentioned. Okay, at least for certain materials, you have to worry about pressure. Like, you know, when I talk to you in this room, of course, the perturbations, the delta fluctuations of the air in this room, the sound waves, are organized by pressure. We don't have to worry too much about a little density perturbation from a sound wave collapsing under gravity. So, but on the other hand, if we looked at, you know, air and systems, clouds of gas on very large scales, you know that eventually gravity will win. And so clearly gravity is playing the central role in this story, but sometimes we'll have to worry about pressure as well. And then finally, we'll have to worry about the expansion of the universe. That plays a critical role in this story too. Right? So we cannot just pretend that this is just some overdensity in an otherwise static universe evolving. So we have actually these three things to worry about to get this story right. Is that okay? Okay, so for example, 10 to the minus 5 we see very directly actually in the fluctuations in the CMB. So related to this picture is the, although we will mainly talk about matter for the next couple of lectures, at least so it's easier, a little bit easier to describe it for the baryons. The baryons are tightly coupled to the photons. And the photons we know have a 10 to the minus 5 level fluctuation because we directly see the CMB. And that is closely connected to a certain level of fluctuations in the matter as well. For baryons, that's easy to imagine because they're coupled. Even for dark matter, we can figure that out too because they're coupled through gravity and so on. So yeah, so there's actually, I just set a range here, but we can actually be very precise as to what the actual numbers are. The reason I'm not precise is because it depends on the wavelength that I pick and so on. But for different wavelengths, we have a good idea as to what the actual value is from our CMB directly, and then from consistency of the equations predicts a certain level of fluctuation for, say, the dark matter and so on. But then you can take that and evolve it under some system of equations to today and see what matches. And this is the number you have to evolve. If you evolve 10 to the minus 7, it won't work out. Okay. So even though gravity will play our central story, I want to go through the equations one by one, where perhaps the most familiar thing to you all is to talk about fluid equations we've just organized by pressure. Maybe who's seen those equations? Who's seen like a fluid dynamics with just pressure, something like that? Like Euler equation, sometimes some version of the Navier-Stokes equation. Okay, we'll start with pressure, and then we'll add gravity, and then add expansion, okay, to get a full set of equations. I could just write down the final equations, but that will look a bit weird as to where they come from if I do it like that. Okay. So any other questions? Okay. So yeah, so we're interested in matter primarily. So non-relativistic stuff. And if you like, you could, for the next, say, couple of lectures, you could imagine that we're interested in the phase of the universe from 47,000 years to about 10 billion years, which is the region when matter dominated, right? Radiation was the first 47,000 years. After about 10 billion, dark energy is starting to dominate. So matter dominates in this era. But actually, the kind of equations that we'll come to, we can more or less use them throughout the whole history, because even if matter is subdominant, I'm choosing to look at the matter component of the universe. I'm interested in the behavior of the baryons and the dark matter, even if they're subdominant. But to organize our thinking for the next lecture or so, you could just imagine this is the total stuff and you're in that window there. So you don't have to pay so much attention to worrying about the other stuff that's floating around conceptually. Okay, so we want to do a kind of fluid analysis. That is to say, we're certainly not interested in writing down the equation for every single dark matter part, or baryon in the universe. So that would be a horrible set of 10 to the 80 coupled equations or something like that. So we're interested in some fluid, okay, like I draw here, some, say, smooth, continuous thing. And organized by a density rho, right, which is, we care that it's a function of space and time. And at each point in space, it can have the fluid can have a velocity that depends on space and time. All right. So let's say you take a region of the universe, and you pay attention to just a little chunk of it here, some little little piece of volume. And if only pressure is at play, so yeah, maybe let's start with maybe mentioning we're going to do, let's say, analysis number 1, where we include pressure, and we're going to ignore gravity, and we're going to ignore expansion for a little while. All right, so we just want to write down some force law for acting on that little piece of material. Right, so this piece has some mass delta m. Right, and it has an acceleration, which we can write dv dt. And let's say we just focus on the x-axis for a moment. So I'll write dvx. All right, so if you have a pressure acting, there's some pressure, which again, I can call a little piece of pressure, a little change in pressure dp in the x direction. So the change in the pressure from here to there along this axis. And then there's something wrong with that. What should I do to make that a force? Is pressure a force? I should multiply by something. What should I multiply it by? Sorry, nice and loud. An area, right. So there's some cross-sectional area here. Let's call that delta A. And this distance here is delta X of our little chunk. So I write some delta A. Nothing too fancy. All right. And let's now divide both sides by the volume of this thing. So we'll divide by delta V. And so this I could write as minus the change in the pressure over just the change in X, because the areas cancel. Okay. Okay, so if we take a continuum limit, we just have that m, right? Well, sorry, delta m, delta v, right? So this is some mass density. I don't need to write m. So mass density rho, delta m, delta v, times the acceleration, is somehow minus the change in the pressure over the change in x, and that's just the change in the x direction. Okay, so for the three-dimensional version of this, we can easily update this to just the velocity vector. Okay, and I can be kind of loose and write dp dx, right? By that, just a shorthand notation for the gradient of the pressure. All right. All right, now this business, the tricky thing here, if you haven't seen it before, is that we don't actually quite want to be writing ddt all the time. Okay, that seems like a fine thing to write, but we don't quite like writing ddt in a sense. For a fluid, if you imagine you have a fluid in front of you, this ddt, what it means is, you see our little fluid element here, you would be tracking how it evolves in time, tracking that little piece of blue as it moves. But often what we want to do is to just look at, say, for example, a point in space and ask, say, how the density or the velocity field changes in time. So if you're interested in that question, you should be doing some kind of partial derivative with respect to time. And then sometimes you're interested in just taking a snapshot of things in time, taking a photograph, and asking how it varies in space. That would be a partial derivative with respect to x. Okay, so we want to sort of eliminate these ddt's, not that there's anything wrong with this per se, but if we think of v here, okay, so as I said before, v is a function of space and time. You want to think, how do you take a derivative of this thing, bearing in mind that the piece of this object itself, x, would be changing in time if you were to track the fluid element. Okay, so if somehow you had a fluid in front of you and you did put a little bit of color blue on a little segment of it and you watch that little blue thing move, you would say, its position is a function of time. Right, so now that makes it a little more awkward. It's like you're thinking of v as a function of x of t comma t, if you were to track it, which we don't want to do. We want to write down partial derivatives. Okay, so if I ask you to take the derivative, the straight derivative ddt of that thing, you want to think of it as a function of two variables, but they both in some sense depend on time. Explicitly time and then implicitly a function of time. Okay, so does anyone know how might I write that? Just a math question. If I give you v of x of t comma t, how can I write ddt of v in terms of partial derivatives?
Partial times the whole thing, and then partial space times partial space.
Okay, ddt of v, so like this. By whole thing, you just mean v? Yeah, and then I can write I think you meant partial space, v, and then maybe I'll sneak in here by the chain rule, the dx dt part that you're referring to. Well, that I could write as dx dt, put a little dot there. So in a way, we should be slightly careful about our dots. Okay, so for example, if you did this for just the x component of acting on a scalar, right, I will put vx there. And then I hope it's clear that the dot product is between these two things. It's not the dot acting on that thing. I can do it for each component. So anyway, I'll put the brackets there to remind you how the dot product acts, and then we can just upgrade it to a vector. Okay, but this thing we can rewrite. This is ddt of v, but this dx dt is nothing other than the velocity itself. Okay, so this is v, and ddx is just a gradient. So I can write grad if I wish, acting on v. Okay, these things have fancy names that I always forget. Convective derivative or something or other, I don't know. Convective derivative. Okay, so with this version, I'll plug it in here. And so now we have rho regular derivative, or what? The partial derivative with respect to time, but then this funny correction, v dot grad. And then it just acts. In this case, we only have a pressure force acting. All right, so this is actually a version of, I guess, Euler equation, E for Euler. And we're just going to be building off this equation as we go. So adding gravity to this equation will be very simple. We'll just add another term on the right-hand side from the gravitational force. Well, let's just keep this for the moment. Any questions about that? Okay, so we're pretty much always going to be dealing with partial derivatives as we go. And then, relatedly, there's a continuity equation, or not, well, separately, I should say, there's a continuity equation, which would, in the Newtonian sense, yeah, so just to be clear, I said everything's non-relativistic, so we're doing a kind of Newtonian analysis. We have a law of local mass conservation, which you can write as d rho dt, plus something we talked about earlier on in the course. You could take the divergence of pi, the momentum density, stated that way, this equation is true whether you refer to the energy density in the full relativistic theory or the mass density and you pick up the non-relativistic momentum density. But the momentum density pi is just the mass density times velocity, right? Momentum is mass times velocity, so momentum density is mass density times velocity. And that's a more useful way of writing this. I don't want to write pi's all the time. So d rho dt plus the divergence of rho v is 0. So this is just a statement of local mass conservation. And this is just a, well, this is just a glorified Newton's second law for a fluid. Okay, so this is our pair of equations. I'll call this one C for continuity. Okay, who's seen these equations before? I'm not seeing these? That's okay. All right, so now what we want to do, you see well, first of all, these equations you see are a bit tricky to solve because they're nonlinear. Right, we see that everywhere. Our variables are the density and the velocity. They're obeying these differential equations. So already here we have a product of rho v. So this is already nonlinear right here. And here you have v and a v. You have a v squared, and then another rho. So actually this is quadratic, this is cubic, and so on. So it's somewhat nonlinear equations. Okay. But don't worry, we're mainly going to do some linearized analysis around some background. Okay, and when the perturbations are at the 10 to the minus 4 level or so, 10 to the minus 5, that's pretty good. Okay, it's only in the late universe where they grow and grow that doesn't quite work anymore. Okay, so let's imagine there is a static homogeneous background. So that I write rho bar, p bar, right? A background density, homogeneous density of some material in a box. Constant pressure in the box is the background. And then you don't really write a v bar, you just set that to 0. So imagine things are just static in the box. There's no velocity at the background level. All very boring. And then we're going to write rho is the background value plus the perturbation, delta rho. So this can be a function of x and t. This is a constant. Pressure, I can write it in the same way. Delta P. And for V, I'm not really writing anything at this moment. I could write delta V, but the background value is 0. So I don't bother to write delta V. I could. But yeah, I mean, I guess I could write delta V. But we're just going to write it using the symbol V. Okay. Is that all right? So we plug that into these equations. So first of all, let's check at the background level, it's a consistent thing to do. The background level pressures are constant, so that's gradient of that is 0. V on the background is 0. So the left-hand side is 0. So we easily get 0 equals 0 on the background. Is that all right? And then if I check this equation, V is 0 on the background, so that's vanishing. And rho is static. So d rho background dt is 0. So every term is 0 on the background. So it's a valid thing to write down. Okay, so our task is to look at the perturbations around this to first order. So any questions? Okay, so we want to work to first order. That means in delta rho or delta p or the delta v, which is just like whole velocity. All right. All right, so let's just write out each piece. Okay, maybe we can start here. D rho dt. Right, the background piece is static, so this is just d dt of delta rho. That's easy. I guess we can write all these things out. The divergence of rho v, okay, from this piece. V is small, so I only need to evaluate rho on the background if I work to first order. So I pull out rho bar, and then I'm left with the divergence of V. And on it goes. Rho dV dt, first term in the Euler equation. V is small, so I can just write rho bar. I could write approximate signs, I suppose. dV dt. Rho V dot grad V, the second term in the Euler equation. V is small, so that's V order V squared, so we can ignore that. So this is 0 plus the stuff we're ignoring. Is that all right? Only care about first order stuff. And then finally, grad P would just be the gradient of the change in the pressure to first order. That equals minus the gradient of delta P. I guess this one is an equal sign if I like. Is everyone comfortable with all these little steps? Everything should be first order. All right. So now let's write down our Euler equation and continuity equation at first order. This one is now just rho bar dV dt, and then minus the gradient of the change in pressure. Right, and the continuity equation is ddt, or I write dt. But all right, sometimes I write dt, just means, means ddt. Acting on delta rho is minus rho bar div v. We can call this is Euler, I don't know, linearized. And this is continuity linearized. At first order, we say we're working to linear order as well. Now, this pair of equations what we're often going to do is, since we have a pair of variables, right? We have our density we're trying to solve for and the velocity we're trying to solve for. We can eliminate one in favor of the other. Okay, so anyone have a strategy? Let's say I want to eliminate the velocity only in favor of the density or delta rho. How can I manipulate these equations to get rid of the v's in them? Yeah. Sorry, sorry. Use conformal time. I don't even wish to be that fancy at this point. Conformal time will play a role between t and a different time if you have expansion, but I don't even have expansion here. So it's just a little mathematical trick. So let me put it this way. When I try to get an equation now for just density, there'll be a price to pay. It's going to be second order in derivatives. Right, so I can trade a pair of first order equations. They're all first order in derivatives. One derivative with respect to x, one derivative with respect to time. I mean, here I guess I could have written dt of v to be consistent with my notation. So I want to make something second order in derivatives. Yeah. Yeah, sounds good. Everyone okay with that? So you try to pick up mixed derivatives. So if I take a divergence of this, of EL, right? So that's rho bar. Space and time derivatives commute. So I could write that as if I like dt div v. And that's minus the divergence of that, so that's a Laplacian, delta p. And then I can also take a time derivative of the continuity equation. Okay, take time derivative of this one. So I get the second time derivative dt squared acting on delta rho is minus rho bar dt div v. So that's the trick. And you see the advantage is that this mixed derivative term, dt dv, is appearing in both. So we can just substitute one into the other. And therefore, this term here, up to some minus sign, must equal that thing there. We combine these, and we get this second order differential equation. But still, we're not done. Right? Because now we have a perturbations in density related to perturbations in pressure. Right? And so we need to link them somehow. Right? So what do we call an equation that might link pressure to other variables like density? I mean, we need to know something about this system. What do we call those equations? Equation of state. Yeah, so let's assume some equation of state. And for simplicity, we'll take P just to be a function of rho. Right? Principle could depend on other things like temperature and so on, but let's imagine it's uniquely determined by the density. And then that implies a little perturbation delta P is just dP d rho times delta rho. Right, just first order Taylor expansion. And this thing in brackets, dP d rho, we can just give that a name. We'll call that CS squared. So this thing is that thing. I'm allowed to call it that. And this is first order. I mean, you can think of this you're expanding around some point, some rho bar, p bar. If you like, you could think of this as evaluated on the background, but it doesn't matter. All right, so altogether, we have dt squared delta rho minus cs squared Laplacian delta rho. Okay, so we got something nice at the end of the day, right? So what do we call these kinds of equations? Basic stuff. Yeah, well, okay, sorry. And then I really should be explicit here. In some sense, we evaluate this on the background because, so remember I write rho is rho bar plus delta rho. And I'm doing a first order expansion around some point, p bar rho bar. So therefore I can evaluate that on the point about which I'm expanding. Does that make sense? And the point I'm expanding is a constant in space because I'm assuming the background is homogeneous, if I wasn't clear about that. Yeah, all right, so questions about this? All right, so we have this bit of manipulation, right? We haven't even yet included gravity and all the fun stuff, but just as a warm-up, these fluid equations lead to a nice wave equation at linear order. And then you know that CS is a good name. That's the speed at which these perturbations propagate at. And since they're driven by pressure, these are just nice compressional waves or sound waves. The CS for sound speed. We could state it like the following. Sometimes we could just write out the solution delta rho, as you know, is maybe a sum of cosines and sines. And where omega k is CS k sound speed. But often going forwards with the kinds of equations we'll get, we want to think of, they'll be a little more fancier than this, although not too bad. We'll often want to think of directly solving them by doing a Fourier transform rather than just declaring that's the answer. So if we do a Fourier transform, I can write that as delta, let's say rho hat for a Fourier transform. It's a function of k and t. Spatial Fourier transform weighted by e to the minus I k dot x. Okay, so with a bit of practice, you will know exactly what that becomes when you Fourier transform it. But if you haven't gone through that exercise before, you want to do it step by step, you can take this equation here, multiply throughout by e to the minus I k dot x, and then integrate d3x, right? So let's just remind you in case anyone hasn't seen it. You just write d3x, this equation, dt squared delta rho. I'm allowed to do that. The integrand is 0, so that whole thing is still 0. And then you see this dt squared factor here commutes with the spatial integral, so you can just take that in front. So then you get dt squared. Without the dt squared, the d3x delta rho is just the Fourier transform. And then the only fun thing to worry about is the Laplacian term. okay? Because the Laplacian, you can integrate by parts. So you push a derivative onto that. And each time you integrate by parts, you'll pull down a plus ik. So you pull down two factors of ik, so that's minus k squared. The minus cancels that, so it becomes plus cs squared, k squared. And once you've moved the Laplacian over, you're just left with the Fourier transform of delta rho. Is that okay? I don't need to go through every one of those steps. So basically, yeah, so you haven't done it before. Whenever you see a Laplacian or minus a Laplacian, just spits out a k squared, plus k squared for minus Laplacian. All right, and so this just reminds you that this equation now is just the equation of a harmonic oscillator. Right, this kind of reminds us of just, x double dot plus omega squared x equals 0 with omega equals CSK, which is indeed the relationship we know is true, the frequency and wave number. Okay, so when we add gravity to this, it's going to be useful that we can do those little steps. So any questions about this? Yeah. Just a good old pressure supported wave or sound wave. All right, so now we want to add gravity. So this is going to be pressure now, plus gravity. In some sense, I kind of mean local gravity. And we're going to somehow be very naughty and ignore the overall gravitational effect on the whole universe. So we're somehow going to ignore expansion. As you know, as we've been studying to death in this course, the dynamics of the expansion is described by gravity. So what we're going to do for the next couple of minutes is not quite consistent, but we'll fix that later on. Okay, so the Euler equation, I'm just going to state it for you. The derivation is basically identical. It's going to look almost the same. Pressure. And then we can include the gravitational force provided by the gradient in the Newton potential. Right, so minus rho grad phi Newton. That's the Newton potential. You see that must be right, even with a prefactor of rho, the mass density. Okay, because if you just focus your attention on gravity only, you see it somehow telling you that this thing, which is a glorified way of writing the acceleration, dv dt, is then just grad phi, right? Minus grad phi. Right? They both multiply rho, the way I've written it. Okay, so you see acceleration is minus grad phi. That's how the Newton potential sets up accelerations. Is that okay? And then with the Poisson equation to specify phi, Laplacian of phi Newton is 4 pi g rho. So this thing is, we have to somehow solve this thing self-consistently. If we imagine, if this is the only fluid, and we're going to have to come back to this later, right? Because we could separate out the contribution to gravity coming from baryons versus dark matter, and even the contribution from radiation. But if we just treat it as a single type of material at this point, then the phi here that provides the force is self-consistently determined by rho itself. There's no other object that we're tracking. And the continuity equation is a statement of mass conservation, so that doesn't change, even when you add gravity. Okay. So all we wish to do now again is to develop the linear equations of motion. And this is the point at which I be a bit sneaky. And we're not going to double check that I have a constant static background. Because when you have gravity, you cannot have a constant static background, right? If I fill the universe with a homogeneous rho bar, and I let it go with zero velocity, it will collapse. So I do not have a constant static background about which I can expand. So we are just going to ignore that and worry about the background in the next class. So we'll pretend that somehow the background equations are valid, even though they're not, and jump straight to the first order equations. Is that okay? It'll give us an idea as to what's going on. So we want to look at the linear or first order equations. And so I'm acting as though I can write this. V again is just V. And then the Newton potential, well, there's some background value, which we're not going to get into at this stage, and then a perturbation. Okay. And we're just going to ignore the fact that phi bar, p bar, and rho bar cannot actually be static for the next few minutes and fix it next time. Is everyone okay with that?
An assumption here about what dark matter does to itself, it must be self-interacting in order to have a pressure.
All right. So yeah, so as we go forwards, we're going to essentially imagine that the pressure associated with dark matter is negligibly small. As far as we know, that's the case. So really, yeah, as I said, we should separate out and have two fluids. We're going to have to label these rows with some index I later on. But there will be significant pressure amongst the baryons, a significant CS, if you like, associated with the baryons. But as far as we know, a negligibly small CS associated with the dark matter. Yeah. And that will mean very different behavior for the baryons versus the dark matter in the early universe, when the baryons will have a big CS. Well, in a way, you could, yeah, I guess you could turn on a CS as big as you want and see at what point it's inconsistent with data. But the current data is more or less consistent with CS of essentially zero. There's a bit more to the story than that, but you can't quite set the CS to zero, but very small. Okay, so the linear equations, I can just write them on the board because all we added to it was this one new term here. Right? So it's very clear if I study this term at linear order, it's just going to be grad of delta phi. And all the other linearizations we did there and there are going to be identical to what we wrote down a few minutes ago. Okay, so for sure we're going to have rho bar and so on. So far, so good. Identical to what I wrote before. And now I just add this one new term from gravity. Delta phi, Newton. Yeah, let's write down we can write down this equation. I just put in a delta phi is married to a delta rho at first order. And the continuity equation is its first order perturbation is completely unchanged. All right. So then we do essentially the same manipulations as last time. Okay, so you want to take a divergence. You're going to take divergence of this thing. And we're going to take a time derivative of this thing. The exact same procedure. Okay, because our the only new things are these phis from gravity. They don't have any v's in them. So our strategy to eliminate the v terms would be the identical same strategy as before. Don't have to do anything new. All right, we can write that very quickly. This one, rho bar. I took a divergence, that's all I'm doing. Laplacian delta p now. And Laplacian of the Newton potential. Okay, I took a divergence of that. Now I take a time derivative of this one. I get that. Those are those two steps. Good. So we insert this into here. Insert. And over here we have the Laplacian of phi Newton. So then we use Poisson. Right, this is the linearized Poisson equation. I should have written delta phi. Is that all right? So we kill the mixed term here, and we use the Poisson equation to eliminate delta phi, Laplacian delta phi. So we can do those little steps, and then you get dt squared delta rho, same as before. Right, and again, I'm writing delta p is cs squared delta rho. And then the only new thing we have is from the Poisson equation here, get minus 4 pi g rho bar delta rho. A bit boring to write it on the board. But is it okay? That's just this one new term. And it's very nice that the Newton potential goes away as well. That trick of taking the divergence of this thing, also converts this into a nice Laplacian, so we can use the Poisson. So that makes it very nice. All right, so explicitly a differential equation, a second order differential equation as before, partial differential equation with time and space derivatives in terms of purely delta rho. And then we just have this new term here, whose prefactor is a constant. Okay. So maybe let's Fourier transform this thing. So again, yeah, it's a delta rho hat. So Fourier transform the whole thing. As I said before, the dt squareds are going to go straight through the spatial integral. Minus Laplacian becomes k squared. Delta rho hat. And this thing is just a constant times delta rho. So that's very simple. So this is our equation, linear perturbations around some background. And we just have to unpack this for the next few minutes. Okay, any questions about this? So we can write it slightly differently. I can just pull out the dt squared term, delta rho hat, and then the other stuff we can put in brackets. Right, 2 time derivatives, and then a constant in k space times delta rho. So you see this looks like a harmonic, kind of looks like a harmonic oscillator. X double dot plus omega squared x equals 0. But now we're no longer sure that this prefactor that I called omega squared, if it's positive or negative. Okay, there's a plus term coming from pressure and a minus term coming from gravity. And this makes sense, right? Pressure likes to push things out, and gravity is an attractive force trying to pull things together. So this is why they're coming with opposite signs. And so if we just think about the structure of this equation, there's 2 possibilities, right? When cs squared k squared minus 4 pi g rho bar is positive, then indeed the omega is some real number. This looks like a harmonic oscillator, and the solutions are just oscillatory. So this limit where cs squared k squared minus 4 pi g rho bar is positive, somehow the pressure term is dominating, right? So when pressure dominates, you should expect a good old sound wave to happen, and gravity is just a little bit of a correction. But then in the other regime where this is negative, really our equation, let's call this case, I don't know, I 2, 1 and 2. Maybe we should write I is kind of like that, but case 2 is somehow x double dot, it's kind of like minus omega squared x equals 0, right? If you flip the sign of that thing, that's a sort of, I don't know, upside down harmonic oscillator. Or if you like, this is more like, you know, a ball near the top of a mountain, and you just perturb it slightly off the top of the mountain, and it wants to roll away. Whatever you want to call that, inverted oscillator, or doesn't matter. Okay, so what kind of solutions do we have for this equation? Some kind of growing solutions, but specifically, what do we have? Exponential. Yeah, so exponential. Some kind of growing solutions. And this is the opposite limit. Somehow this is the term where gravity is more playing a bigger role than pressure. And that's what you expect gravity to do. If you have slight overdensity, it wants to become more overdense over time. The system wants to collapse, which means its density goes up. So this is related to gravitational collapse. Well, it's linear theory, so maybe we can't track it all the way till it fully collapses, but it's the first phase of that collapse that we can track using these equations. So think of this as some big dust cloud out there on some large scales. Eventually, gravity can beat the pressure force, and it may start to collapse. We haven't included expansion, so we can't, as I said, strictly speaking, apply this to our whole universe, but this kind of separation will play a central role there too. Question, yeah.
Get a sense of physical intuition for the harmonic oscillator and the expansion in Fourier transform.
That's right.
But how does that correspond to the actual, harmonic oscillator?
Well, maybe let's write out this solution for a minute and then we can unpack that. Okay, so let's say we look at case one. Well, I also want to just if I can define one thing for a second. You can see there's a distinction before we answer your question. Let's define there's a special wave number, which is the boundary between these two cases. So that is the square root of this. Okay, I guess I don't need the CS in the square root. And this thing is called the Jeans wave number. So again, the statement, therefore, is that K greater than K Jeans, pressure wins. You have oscillations. And K less than K Jeans, gravity wins. And you have growth. Growth in the density. You can also think of this case as being that where the perturbations are stable. Right? You perturb your system away from equilibrium and it just oscillates and it likes to go back towards equilibrium and oscillates around it. And this is the case where you perturb your system away from equilibrium and it loves it. Now it just keeps on growing if the exponential hits. So the system is unstable. Likes to run away from equilibrium, the homogeneous equilibrium. Now we can check, by the way, that this is happening therefore on different length scales. Right? So we could imagine our perturbation has all sorts of different modes, some short wavelength, some long wavelength. And we're seeing here that high wave number, which is short wavelength, pressure wins, and small wave number, or long wavelength, gravity wins. Remember, wavelength is 2 pi over K. Okay, so this is also a long wavelength case. This is the small wavelength. Okay, this is, if you like, that's this case, and this is long wavelengths. Case one versus case two. So who can tell me why does this make sense? Somehow small wavelengths are dominated by pressure and long wavelengths, gravity's winning. How can we summarize the reason for that? What does that remind you of a very basic property, let's say, of gravity? How do we sometimes describe the force of gravity? Small wavelengths have more energy. So you mean, therefore, pressure should win somehow? Provides more pressure, maybe? Okay, that's a possibility. And what else can we say? Yeah. Oh. Right.
Wavelength. And then regime that it's like, well, I don't know how to describe it. It's just that it's a wave and it goes down in potential hill and up.
Right, but let's be careful because in this system here, the gravity and the density perturbation are the same thing. Like that one determines the other. So therefore, if you tell me you have like a well, that's a form of delta rho or delta phi. Do you see what I mean? They're all the same thing. Does that make sense? Okay, sorry. Do you want to, yeah. Yeah. Yeah, that's right. This is the simplest answer I'm aware of. Yeah, gravity is long-range force, so the long wavelengths are dominated by gravity. And pressure force, you can think of as like in the air in this room is kind of the air molecules at some level bang into one another. It's a short-range force. So that's why you have this separation as to which one wins. All right, now let's just write down the solution, the explicit time dependence of this, okay, which hopefully will answer your question. So we're writing down things explicitly in K-space, having Fourier transformed. And our equations just become this nice ODE. So in case one, we can just say the general solution for delta rho is some prefactor A, for example, cosine omega kt plus B sine omega kt, omega k is this thing. And this is really, truth is a function of k, right? So I should really put like a little k subscript, the function of k and t. So these are the Fourier amplitudes, which can depend on k. And then if you give me, remember, if you give me a bunch of these numbers, you can just make them up, or they're set by your choice of initial conditions. Then you can just unpack the actual perturbation back in position space by, again, just doing the Fourier transform, or the inverse Fourier transform, I guess. Is that all right? I mean, I can write k explicitly, k comma t, or you can put a subscript. It doesn't matter too much. Is that all right? So every one of the Fourier modes would just oscillate. And then the full theory, is just a sum or integral over all those Fourier modes. And then in case two, the solution now is going to be exponential. So I could call the coefficients, I can still call them A and B, it doesn't matter, or I can call them C and D or something. Doesn't matter what you call the coefficients. We can write e to the omega kt. And we should also not forget that we can have a decaying mode, minus omega kt. It's also a solution of this equation. And here I'm defining omega, or maybe you want to give it a different name, but I'm going to call it omega. And I've just flipped these around. Maybe you want to, not everyone would like to use the letter omega now because it reminds us of a frequency of oscillation, but it's just the name I'm giving to the exponent. So anyway, does that answer your question? So every Fourier mode is just the sum of an exponential and decaying exponential. If you wait long enough, that means this second piece you could ignore, and this will be the one that will dominate at late times. And every Fourier mode obeys that with a different omega. And then you have to always do the Fourier transform if you want to see things back in position space. But every mode is growing like this. Okay, well, really the full solution, we should just combine the two, right? So this is what we do for k greater than k genes, and this is what we do for k less than k genes. Okay, so you have to put it all together. So when you do the Fourier transform, which is an integral over all k, you should split it into two pieces, the k less than k genes bit and the k bigger than k genes bit, and sum all that up. Okay, so that's just what's going to happen. So you imagine you lay down initial conditions of some complicated mess, and some of those modes, the short wavelength modes, will just oscillate, and the long wavelength modes will grow. You have these two effects going on simultaneously for generic initial conditions. All right. Any questions about this? Okay, so if not, we'll work on putting back expansion in for next time. All right, thank you.
Equations
The physics of, yeah, it's very similar.
are.
I guess so. Very similar equations, that's true.